Hello, everyone. Today we'll be going over 2023 FTC Camera Vision Workshop through TensorFlow. So our table of contents will start with VisionPortal, going through its application, usages, plus a demo. Then AprilTag plus White Pixel demo, custom TensorFlow Lite model, and then applications in the game. So first is a machine learning overview. Machine learning is a branch of artificial intelligence and computer science, which focuses on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. So some types of machine learning include supervised learning, which uses a labeled data set, unsupervised learning, unlabeled data set without any guidance, semi-supervised learning, which is labeled data to ground predictions, reinforcement learning, which is autonomous, and it's a self-teaching system. And for today, we'll be using supervised learning. So first, second, we'll go through VisionPortal. What is it? So VisionPortal is a new interface for vision processing provided in version 9.0. And some of the tools include capabilities of AprilTag, Easy OpenCV, and TensorFlow object detection. Some features of VisionPortal include AprilTag detection, which provides data on ID and pose tags position/location with regards to the camera controls plus multiple cameras, which is the capability to use multiple cameras at the same time, and TensorFlow object detection, whether you utilize this season's pre-trained model or create your own custom model. And so first, open the basic op-mode linear project from your external samples, and then import these import statements. And then for the webcam, after the class declaration, add these pieces of code.
Okay, so at this point, we're going to go over the AprilTag and White Pixel demo. So to initialize the code for your AprilTag processor, after the wait for start function in the VisionPortal, you want to create your AprilTag processor with the following code snippet. And then you want to create the VisionPortal with the AprilTag processor as shown on the slides. And then inside the while op mode is active statement in the code, you want to initialize this list of detections, which will get all the detections from the AprilTag processor. And you want to print these out to telemetry with the following statement. And at this point, you can iterate through this list of detections that you've made, and you can get a bunch of different information, like the ID, the pose, and this pose can consist of a bunch of different stuff like the range, bearing, and yaw. And you want to make sure that at the end of your statement, you add a sleep for 50 milliseconds so the machine does not overload. So some of the AprilTag poses that you can get from the detection, there's the XYZ, and you can also get the pitch, roll, and yaw, which is all important information.
Okay, so this is how you can interpret the tag pose. So the tag pose is a combination of the relative position from the camera lens center to the April tag center, and also the orientation of the April tag in the camera's reference frame. So starting with position, it consists of X, Y, and Z, where X is like the direction to the right, that's perpendicular to the Y axis. Y is straight outward from the camera lens center, and Z goes upwards and perpendicular to X and Y. And you can see in this image to the right, where the X line moves from the right of the center. The Y line is not shown, but it goes from the lens center, and the Z line moves upward. And then orientation consists of pitch, roll, and yaw, where pitch is the rotation along the y-axis, and roll is the rotation on the x-axis, and yaw is the rotation on the z-axis. Lastly, there's FTC's calculated extension of the basic pose, which starts with range, which is the direct distance to the tag center, bearing, which is the angle that the camera must turn either left or right to the point directly at the tag center. And then lastly, elevation, which is the angle that the camera must tilt either up or down to point directly at the tag center. Okay, and then the other option is to use the VisionPortal for recognizing the white pixels using the TensorFlow object detection processor. So here's like the initialization code. So similar to the April tag processor, after the wait for start, you would create the TensorFlow object detection processor using this line of code, and then you would create the VisionPortal with the TensorFlow object detection processor. And here's like the code to iterate through the detections. This is also similar to the iteration of detections for the April tag. Here's what it looks like to test your code. You would be able to see the lines of code that you use to print out the number of detections, as well as like the labels for the recognized objects and the confidence score. And then here's some other useful methods that you can consider using. Some of these includes like the VisionPortal.close, which basically tears down the camera processing and closes the USB connection with the camera by calling like stop streaming.
So now we'll kind of go over how to build a custom TensorFlow model if you want to detect your own unique objects. So to kind of just briefly go over what I guess a custom TensorFlow model entails. TensorFlow is essentially an open source machine learning framework that's designed to make the development and training of custom machine learning models really easy and generalized for the user. It contains pre-processed data sets and tools to help optimize the training process. And it's very scalable and easy for a lot of people to use. And common uses of TensorFlow are object detection, image classification, so on. But we're really going to be using it for object detection today. So to set up a custom TensorFlow model with the first machine learning toolchain, first, you can go to the link that is attached on the slides, ftc-ml.firstinspires.org, and you can log in with your first account. For CHS students who are, a part of Cupertino Robotics, you can contact Mr. Williams to gain access to the dashboard, and you can contact us in person if you need help with this process. After you've successfully made it into the toolchain and you are now able to upload data, when you're loading in your data, you want to make sure you're optimizing the data that you're uploading. So you want to make sure that whatever videos you're putting in are like the same conditions that you would have your robot looking at. And limiting the frames per second can help you get a better and clear image on your data. So here is an example of a video upload. As you can see, it approaches the object in question, the yellow pixel, from a bunch of different orientations and positions in the camera. And there are some tips for Mac users to take videos. For Windows users, it should be fairly self-explanatory using the camera app. But there's also instructions online. So at this point, you probably have your data uploaded, and now you're going to be confronted with the next part of the machine learning toolchain, which is labeling your data. So like Abhinab mentioned earlier, we're going to be working with supervised learning in this process. And so to label the data allows the models to help categorize and also detect these objects. So through this, you have to add bounding boxes onto your object in question. And FTC ML toolchain has a really convenient tracking API that can help you automate the bounding box based on predictions of movement. So on the actual FTC ML toolchain website, or like kind of breakdown, there's a more in-depth explanation of every single aspect of the interface. but here we just labeled 5 important things, and those numbers are the same as the ones that are in the image. So like the one that has 1 next to it with an arrow is the same, is referring to the thing that we put a 1 next to. So like it is for tracking loaded frames, for example. So after you fully label the first image with all the objects that you want to detect, and you have drawn all your bounding boxes, you can click Start Tracking, and then its tracking API will track that bounded object for you based on the general motion of the camera and everything. However, it is inconsistent, and so what you'll get is sometimes you'll be able to see how many frames have not had anything tracked in it, and it will not allow you to finish uploading the data without all the frames being tracked and there being a bounding box assigned with all the labels for every single frame. So you can pause this tracking at any time and correct any inaccuracies, or if there are any frames that don't have any bounding boxes on them, you can add or correct these bounding boxes by adjusting the black dots in the corners. So at this point, you've probably uploaded your data, your video, and now you want to make that video into a data set for your model to use as input. So you want to select one or more of your recorded videos and click Produce Dataset. It's in a little pop-up that shows up. You want to establish the train and test split for your data set because a certain amount of data is allotted to train the model and a certain amount of data is allotted to test the model. You can add a description to this data set and just wait till the progress bar finishes and you've successfully uploaded your data set. And there's a few things to consider on the slides. So just one thing that is really important is make sure that, the data set has to contain at least one label or element to track. And if you're selecting multiple videos to put into your data set, make sure they all have the same set of labels. So to kind of condense what's on the slide, after you have your data set, then you want to select the Start Training button. And it'll give you a default model, which says SSD 320 by 320. For anyone who is curious, SSD stands for Single Shot Detection Model. And it's basically a really fast and convenient one-pass object detection model. You can find more online, and there's a little description on the slides. At this point, you can also set the number of steps that you want your model to train with. This is essentially the work unit for the training model. And the amount of steps, the calculation is also linked on the slides. It's a little like latex expression on the slides. And you can also set the maximum training time so you can cap the training process. So let's say, for example, you only want to train for 30 minutes. You can set that maximum training time so it'll cut off the model after 30 minutes of training. You can add a description to your model and then press Start Training. And you can cancel the training process at any moment. I think there's a Stop Training button. And FTC ML will do the calculations for the number of steps and allow you to individually tweak some of these things for you. And these are less important, but if you ever at any moment something goes wrong with the training of your model and you're not sure what exactly, these job codes are kind of your Bible to help debug or kind of figure out what the situation is. So every 100 training steps, model metrics are saved in checkpoints, which are essentially, these bundles of information that you can look at to kind of get a status update. So if your model has failed in between checkpoints, you can refer to one of the job codes, and that's how you know that something has gone wrong. And maybe there's something wrong with the data you fed, or maybe there's something wrong with the training process. That can all be deduced by the job codes. There's a link attached to see some training and testing statistics of the models on the slides. And you can go to the Monitor Training tab for a specific model to see these metrics in raw, graphical, or visual form. A slight disclaimer is that training takes around 60 minutes for 3,000 steps, so plan accordingly. So after you finish training, you want to click on a link to model under description column, which will show the details on the training process and will allow you to step-by-step see what the actual bounding box was and what the predicted bounding box was. And this allows you to essentially see the efficiency of your model. So at this point, if you want to import these models into code, you can download the model off of the FTC ML toolchain as a TF Lite file, and you can add to your assets folder in your project. If you don't have an assets folder, you can just make one. And then you add this TF Lite file into it. Then you go to the Java folder in your FTC robot controller project. In your you go to the external samples file, and then you find the concept TensorFlow object detection.java file. And then you add it to the team code folder and comment out at disabled.
Okay, and then the next step is to add the labels to the appropriate part of the sample code. The line of code is shown here, and so one tip is to use the same label name that you used to label the objects in your model in the previous step, and also to make sure that the labels are in alphabetical order as listed in the description. Additionally, make sure to add the directory of the model that you downloaded previously. And these are two options for adding the model file. The first option here is used when you're storing models in the assets folder, and the second option is used when uploading models directly to the robot controller. So we're going to be, in our workshop, we used the line of code with the green dot since we downloaded the model as an asset. And then here, we're initializing the TensorFlow object detection processor.builder. So be sure to uncomment this block of code. And so for the set model asset name method, be sure to use the set model asset name method as well as the set model file name if you've done. Sorry, could I start this slide over?
Yeah.
I'm so sorry. I did not read this part in advance.
No, it's okay. I'm probably gonna mess it too.
Okay. Okay, so I'll start this slide over. Go. So next we'll be initializing the TensorFlow object detection processor.builder. So we'll specifically be using the lines with the green dot since we are downloading the model as an asset. And so the two lines with the green dot are the set model asset name, as well as the set is model TensorFlow 2. Or sorry, oh my God, I messed up again. I'll start over again. Okay, go. So next we'll be initializing the TensorFlow object detection processor.builder, and we'll specifically be using the two lines with the green dot since we are downloading the model as an asset. The first line is the set model asset name, and the second line is the set model labels. And you would be using the set model asset name method if the custom TensorFlow model is built in as an asset, and you'd be using the second line set model file name if you have downloaded a custom team model to the robot controller. So you would be using one of these depending on how you downloaded your model previously.
So after creating a custom model and adding it to your code, it's important to understand how to apply it into a game setting. So some applications can include, during the autonomous period, recognizing a team prop using the custom TensorFlow model, regarding odometry, figuring out the robot's position and location on the field in regard to the backdrop, determining angle and distance to move towards the backdrop to score in position corresponding to the AprilTag ID, and also determining the location of a team prop / white pixel on the spike mark at the start of the autonomous period. Some of these resources you can check out, including a TensorFlow object detection sample op mode with Java Builder and Java Easy Sample op mode. So Finally, some applications in real life just to ponder on. Some include video surveillance, detecting objects or people within a live streaming video, or even Alexa. In each time you make a mistake, Alexa utilizes that data to make the system smarter next time around. So just machine learning in real life and beyond, just robotics.